Please welcome Mr. ShaikBepari Mohmmed KhajaMoinuddin. He is a PhD student at NMCAD Lab IISc and has obtained his master's in aerospace engineering also from IISc. He is currently working on the buckling of hyperelastic shells and has previously worked on delamination detection in composite beams.
Hi, everyone. So, I'll be presenting my work in two parts. First part will be the part of my PhD work, and the part two will be a small project that is on delamination. So, part one will cover the buckling of hyperelastic shells. Yeah, so I'll just go through the introduction, aim, and some theory behind this of hyperelasticity and what is constructive modeling and what are the materials and experiments I have done on these materials. And how do I model them for buckling using variational asymptotic method. And I'll be presenting zeroth order and first order results. And then I'll take them forward for the 2D nonlinear surface analysis. Then I'll show some buckling mode shapes of wrinkles on these membranes. So membranes, they are very unstable in compression because they are very weak flexural modulus. So they form patterns on the surface called as wrinkles when they undergo loadings. So many a times wrinkles are an unwanted phenomenon that we don't want it because it alters the usual functioning of the structure. So, and this wrinkling is a key problem in ultra lightweight and ultra large high precision space membrane structures. For example, inflatable membranes, inflatable antennas, solar sails, and high altitude airships. So where we don't want wrinkles. So these wavelengths of wrinkles can interfere with the operational wavelengths of the electromagnetic waves. So now in a stretcher sheet, when we stretch a sheet, wrinkles form a regular pattern. That is because of the inability to accommodate the Poisson effect that is coming in the transverse direction. So these are some of the, this is an inflatable antenna figure, and this is a high altitude airship. Inflatable antenna is, because to save the volume in the rocket space vehicle. So you deflate it and you inflate it when it is at the operational space. So there also we get across this membranes and wrinkles form there. So and in high altitude airship, this is also a very interesting concept to replace the geostationary satellite. So if we can maintain a balloon at an altitude of around 20 to 25 kilometers, then this will exactly work as a geostationary satellite. So while designing this also, wrinkles are important for designing the skin and all. So it has various applications. Here one application I show is, this is high altitude airships are flying in the air. They can be used as air traffic control, can be used for survey. Application that can be a platform in the air. Is functional layer, the outer, middle, and the inner layer. So the outer layer is for UV resistant gas barrier, and the middle layer is the strength providing layer. This is a middle layer, and the inner layer is also a gas barrier. For example, in the high altitude airship. So now, what is the aim of this work? So we want to design the skin of high altitude airship subject to wrinkles. That means we want to design the skin and the stiffness placing and all subject to wrinkles. So as we want to reduce wrinkles on the surfaces. So for that we need to first select the suitable candidate materials and mostly hyperelastic because they undergo large deformation so when they are inflated. And so when we select, we have to mechanically characterize the material. So that's called as constitutive modeling. And we have to evaluate the wrinkles using one. So first, I'll just introduce what is hyperelasticity. The word hyper itself is saying it is hyperelastic. It's more elastic. That is, large deformations are coming, and it's Cauchy elastic also. Cauchy elastic are the materials which are history independent materials that don't depend on the history, like viscoelastic and all. So, and they introduce geometric nonlinearity in the stress strain curve. So now if we define a hyperelastic material, so a material is hyperelastic if there exists a strain energy density function W, which is a function of F. What is F? Small x are the points in the undeformed and the deformed configurations of a solid. So if there exists a W, which is a function of F, defined per unit work, such that we are able to get the stress out of this derivative, then that material is called hyperelastic. So if it is a isothermal case, then W will be the Helmholtz free energy, and if it is isentropic case, W will be internal energy. In our case, W is taken as Helmholtz free energy, isothermal conditions. So some objectivity conditions have to be applied on the strain energy density functions. If the observer is changing, then the W should not change. So F plus is a F observed by one observer. So he is rotated. So that is given by QF. Q is the orthogonal tensor that just transfers the tensor F. So now F can be decomposed into the rotational and the translational component R into U. And if you select special R, rotational R, such that R is Q transpose, then Q transpose will be I because Q is orthogonal tensor. So W will just become the function of the translation W U. And to do that, you can define W as a function of C, where C is a right Cauchy Green tensor, which is F transpose F. Okay. So with this we can give the constitutive relation that second Piola Kirchhoff stress can be given by this. So with the representation theorem of invariance, what it says is if you can if you rotate the strain energy, the C, and if they are same, then you can express the strain energy in terms of invariance of C. So we are going to use all these concepts now. Actually, that's why I want to present some basic theory. And it should satisfy the normalization condition, that is the strain energy in the initial stage, undeformed stage I, that is when F is I, it should be 0. And when F is there, it should be greater than 0. Now, if there is a material with two families of fibers, that is, I was talking about the isotropic material, if we go for orthotropic or transversely isotropic, then, and for especially for a case of two families of fibers, then I need to, prove this so that it has to be same when I rotate each quantity. And indeed, they can be proved. Then we can represent the strain energy in terms of 9 invariants for a general case of two families of fibers, where the invariants are given by I1, I2, I3, I4, I8. So it is trace of C, trace of C square, and so on. A naught and B naught are the unit vectors along the fibers. These are the five unit vectors, and lambdas are the principal stretches. So they are defined like the final length to the initial length. So they are always greater than 1. So mostly materials are incompressible. So we need to enforce this incompressibility constraint on If it is for isotropic, then the form of strain energy will be this, and for orthotropic, it will be this. So finally, after having the strain energy, we need to define the stress, because that is what we are going to use in our experiments, the Cauchy stress. So Cauchy stress for the isotropic and the two families of fiber material are given by these two expressions. Now, what is constitutive modeling actually? Constitutive model relates a stress to a strain. So that is the input and response. So that is a constitutive model, and that is a function of material constants. So our exercise is to find the material constants. Here, because the material is nonlinear, geometrically nonlinear, we have to do that at the strain energy level, in the case of hyperelasticity. So now there is a challenge. What is the challenge? The strain, the function, the constraints laid on the strain energy density function from the coming from the continuum mechanics are very general. Like the principle of objectivity and material frame indifference, they all finally say that if the strain energy is a function of invariance, then it will satisfy principle of objectivity. It will satisfy the material frame indifference. So there is no specific form that is coming from the continuum mechanics. So that's why it's a very general constraint. So we don't have a specific form for some material. This is going to be very challenging. Some materials I'm showing from the literature. For isotropic, so let's say neo-Hookean model, it looks like this: C1 into I1 minus 3 and C1 positive. And for Moone-Rivlin, the function of strain energy will be like this: I1, I2, and it is a product of I1, I2. And these are the constraints. So how these constraints are coming, I'll just tell in the next few slides. For anisotropic, a GO model is used here in my problem also. That looks like this. It has C1, C2, C3, I1, I2, I1, I2 product, and some anisotropy part. This is isotropy part and the anisotropy part also. So we also have to take care of constitutive inequalities. What are these actually? The principle of objectivity and material frame indifference, they are not they are not giving information about the direction of loading. That means response, is it in monotone with the input? So this direction is not explicit from these constraints. So therefore we have to go for some special inequalities, that the strain energy function that we are designing, that should take care of the monotone of the response also. So some inequalities like Baker-Erickson inequalities, tension extension inequalities, all these actually are the general form of Coleman-Knoll inequalities. We say that the direction of stress and the stretch should be same. That means if you are stretching, then the stretch also should be in the same direction. So we have to take care of this. So the Cauchy stress using the representation theorem is given by this. So finally, those E inequalities will boil down to these three inequalities. So while you are designing the strain energy, you have to take care of these also. And these are inequalities. So Kunduker conditions optimization has to be used. So what are the materials I used here? So for the inner and the outer layers, I used Kapton HN. What is Kapton HN? And I'll be telling more in the coming slides. So middle layer, I used Nomex, and I have also fabricated a composite out of this too, by sandwiching the Nomex in the middle, Kapton in the top and bottom. So three materials I'm testing and giving the constitutive laws for that. So composite is fabricated by putting Nomex in the middle and Kaptons on the top and bottom using araldite, like resin. So looking closely at these materials, what are these materials? So chemically, Kapton is polyimide and Nomex is polyaramide. So these are the commercial forms, and we got it from DuPont. the thickness of Capton is 25 micron, very thin, very thin. And the Nomex is 0.5 mm. So elongation given by the supplier is 70%, 22%, and 17%. Actually, Nomex is a transversely isotropic material. So they have two different properties. The Kapton is isotropic material. So the tensile modulus given by that is 2.3. This is very high for that very thin material. So this also makes Kapton very potential candidate for these applications. It can take loads. And also the upper working temperature. So 360 temperature degrees centigrade is also quite high. It can work. So it can be applied in inflatable antennas and used as a gas barrier in HAS. And Nomex can be used as thermal insulator in spacecraft, high altitude airships. So just these materials can be used in different applications. But for a case study, we are just going ahead with this. So here I'm showing the three materials, the samples I have got. The top one is the Kapton sample, white is Nomex, and the third one is the composite. So, and with these these are the aluminum tabs that you can see. So these are the specimens prepared for uniaxial tensile experiments. So two of them I used 25 kilonewton BIS UTM machine, and Kapton is used in this biaxial structure, but I have used only two because stiffness is quite less, so 25-pound load cell was sufficient for this. And here it was a 25 kilonewton, so these two materials were quite stiff. So after fabricating the composite, the quality assessment was done by using X-rays. So you can see these black pictures. So what you can see, these are actually what you call this epoxy that is actually shown. So we can say that X-rays are opaque to epoxy, and this also shows the homogeneity how the epoxy is laid when we are fabricating the composite. So this is how the quality is assessed. A uniaxial tension test are done till failure. Following these are the ASTM standards we followed. D88212, D82816, 82816, same for Nomex and composite. So sample dimensions are 100 mm to the 10 mm wide and 25 micron thin. So here it is 100 mm long, 25.4 mm wide, 0.5 mm thick. So these dimensions are taken from these ASTM standards. We used end tabs for Nomex and composite because they are stiff, and we used iodide to fix it. So this is a test setup. The entire setup was recorded using a camera, high definition camera, and we keep beads on the medium to measure the strains. So we use the image processing of this experiment to calculate the deformation gradient tensor, because we are calculating the strain finally, that is it's going to be nonlinear. So our aim is to calculate the deformation gradient tensor. So loads are taken from the calibrated load cell that we get directly from the load data. So, but the deformations are calculated by tracking the dots using image processing, and that is done using the isoparametric mapping and with the in-house code in MATLAB. So using this formula, this is a standard formula. F is equal to I plus 10 U by del X. So where U is the distance between two instantaneous dots. So we are forming the quad element by joining any four dots. As the four dots move, the quadrilateral deforms. So we map it to the parent element, get the strains, and get the F and calculate C. Then you will get the Green Lagrange strain. So this is nonlinear strain. Finally, we are getting, and with that we can also calculate the stretches. Alpha is one runs from 1 to 2. So lambda 1 and lambda 2. So stretches in two directions you can get using this formula. Now, for the uniaxial experiment, if we want to reduce the, we have to reduce the what you call the kinematics. So the volume change is 1 here. The volume is 1 here. That is, no volume is changed. So therefore, using this, we can, eliminate lambda 2 and lambda 3 for isotopic case. And your right Cauchy Green tensor will just be a matrix of diagonal lambda 1 square, 1 by lambda 1, 1 by lambda 1. So finally, we'll be using this for calculating the Cauchy stress, and we'll fit that in the experiment. So we minimize the error, using subject to the empirical inequalities, using F min con. And finally, we'll be getting the minimum optimized curve. So first we tested, this is the test results, the uniaxial test results. So the Cauchy stress in MP are plotted in y-axis and longitudinal stretch in the other direction in x-axis. So here it is transverse stretch, because Nomex and Composite are transversely isotropic. So we have to test in two different directions. So you can see that Kapton is failing around 18%, and Nomex is around more than 20%, and Composite is just between them. And also the Composite, because it is fabricated from the Nomex and Composite, it has to lie in between theoretically the Nomex and the Composite, and that is almost in between that. There may be some errors. That similarly, you can see that in the transverse direction, that Composite is mostly dominated by the properties of Nomex. And these are the properties of elastic moduli we got. And this also, the Composite in longitudinal direction lies between the Kapton modulus and the Nomex modulus. Similarly, Composite in transverse direction lies between the Kapton and the transverse Nomex in the transverse direction, almost with the standard deviation. Similarly, Poisson's ratio and the elongation at the rupture. So this we have done. Now we are going to give some model fits for the incompressible thing. So this is a Kapton data. So the bubbles are the experimental data, and we have used a Yo model to fit the Kapton. Oh yeah, this is a Yo model. So this is a Yo model. That is a function, that is a polynomial of I1 minus 3 running from 1 to n. So till 5, I varied from 2 to 5. So that's what I'm showing in this slide. So 2 terms, 3, 4, 5. So it is, slowly getting converged to whatever the experimental data is. So the 5-term Yo model gave me the exactly fit the exact experimental data. And also I gave the compressible model also for 2 terms. So this is minus C1 log I3. This plot, I have to design this actually. Some different functions which is fitting that subject to those constraints. So that way I found out that for two terms, compressible is the red one, and the 2 terms incompressible is the green one, are shown like this. So the R square value is around 0.9, not so bad, but not so good also. But this is exactly fitting for 5 terms. So I'm using this Python model and going ahead with the simulation also. And these are the properties of the Python Kapton model. So R square values, you can see they're exactly 0.99, giving for 3 samples, 3 best samples, although we have done so many samples, but 3 best we have taken. So Nomex is very interesting actually. I said already it's a transversely isotropic material. We have done the SEM images on Nomex, taking microtome cutting. What is it?
It's not get to this. It is not connected.
So images of nomex at different locations at different resolutions are taken and observed closely. So we see, fibers are oriented symmetrically as we go closer and closer. So 100 micron resolution here, and this is 20 micron resolution. You see the two fibers are symmetrically oriented. It's a very interesting material. So, and what we did is we tried to calculate the fiber angles of these two. What are those two families of fibers? So we plotted a what do you call this probability distribution curve, and we got two peaks at 69.3 mean with a plus or minus 7.4 degrees, and the other at 129 degrees plus or minus 5.3. So this is almost like 60 plus 60 and minus 60. 60, 120 is 6 plus 60 and minus 60. So what we did is, this is experimental observation. Theoretically, we want to give the model now, model of strain energy. So where we have to input this the fiber angle also. Instead of giving it, we just kept it as a the curve fitting parameter, and we try to get the value from optimization, and that is matching with what the experiment is showing. So this is a fit actually, the HGO model we are using. I don't know if you're seeing the cursor here, HGO model. So this model in two different directions. It's quite a nice fit in two directions, longitudinal direction and the transverse direction of norms. So this table is giving the information that apart from C1, C2, C3, K1, K2 unknowns, I am just putting theta also as unknown. And I'm trying to get theta from the curve optimization algorithm, and that is nearly 55.8. That is almost lying in the range of what experiment is showing. So this is also an interesting thing that we found here in our study. Finally, we have to give the model for composite also. Composite, we did not do it separately. What we did, because composite is taken from Kapton and Nomex, we just try to see if we can superpose the energies of the Kapton and Nomex and see if they can give the response of Kapton. The composite. So energies, ideally, if two systems are gathered, then the sum of their energies should tell the dynamics of the system. So, but with lots of assumptions here, the glue is there, araldite is there, and isothermal conditions are also there. But we are neglecting it. Let's see, with neglecting how well it will fit. It will predict the response of composite. So that's what we saw. Because they are strain energies are defined per unit volume. We have to multiply with the volume fractions. So this looked like a rule of mixtures formula, although it's not a rule of mixtures formula, but it's the energy superposition principle that's very powerful actually. So we try to superpose the energies of Kapton and Nomex, and we found the volume fractions from the experiment. These are the composite data in transverse and the longitudinal directions. It is almost fitting well in the longitudinal direction, and transversely it is not fitting well after some time. So well, these studies, we can say that because the glue is not there and some more things we are not considered, this can be attributed to that. But still, we got a good R-square value. Now, how do we model? We have strain energies now. Now we have to model it for buckling. Now we have to get the buckling of this membrane. So I used WAM. What is WAM? WAM is variational asymptotic method proposed by Bodichevsky in 1979 for nonlinear shell theories. It's a very powerful mathematical tool to find the stationary points of the functional subject to some constraints with an identifiable small parameters, be it geometric or physical. So asymptotics here are applied for the functional rather than the differential equations, in which is less prone to errors. And also it is mostly applicable for the dimensionally reducible structures like plates, beams. So 3D, though we'll be doing 3D, but we'll split the problem into 2D and 1D. Finally, we'll reduce the dimension and we can handle the 3D problem at the 2D level. So this is the advantage of WAM actually. So it involves no ad hoc assumptions. So some let's say how do we do this WAM? Let R of xi and delta be a functional, where xi is the energy density function of 3D coordinates and delta is a small parameter. So now to obtain the stationary point of a functional, first what we do, we decompose in an asymptotic manner. We apply asymptotics and we decompose it into the zeroth order and the higher order. So then where this is the zeroth order and the higher order. So after that, in the zeroth order, we have an unknown z naught, which is a function 3D function. We try to find out that which is unknown, minimize that function, and try to find the stationary points. Apply the variational calculus, minimize that r with respect to z naught, and get the r naught. So this strain energy function, we say that it is accurate up to zeroth order. We have not used any assumption actually. It just variational calculus is used. So the solution is finally eliminating the 3D function in terms of 2Ds. So the 3D function can be expressed in terms of 2D functions using this actually, because Z naught is the 3D function here and all others are the 2D functions. So if you substitute that, then you will get the first order again. So you want to do that repeatedly, that we got a zeroth order. Now we want the first order. So what we do again, minimize this R with respect to Z1 and get R1 again. So then that will be R0 plus R1. So this will keep go on up to the required order. So zeroth order, first order, second order. So that's how WAM works. And here I'm using a plate kinematics and the geometric nonlinear elastic plate theory proposed by Hodges in 1993. So here we are keeping a frame O, inertial frame O, and this is a plate having in the undeformed state with three orthogonal places B1, B2, B3, and this is deformed now. That transforms to capital B's. So small b's are undeformed, capital B's are deformed bases. So if you want to point any point in the at the middle of the plate, then R is a vector for that. And if you go above and the below of the mid plane, then the R hat is given by that. Therefore, R hat is a 3D function. R is a just 2D function, R vector. So that translation is shown as U, which is a 2D function. And now we are allowing all possible deformations. We are allowing for warpings also. So these warpings are shown here. W1, B1, W2, B2, W3, B3 also. So this is a very general and geometric nonlinear formulation. So the capital B's and small b's are related with the rotation matrix C. Okay, and the relation R hat is related to R with just the vector addition of R hat is R plus X3 B3. So that's what it is in undeformed configuration. And in the deformed configuration, R hat is R plus H3 B3 plus the warping contribution. So just vector addition. And we'll be using all this to calculate the deformation gradient tensor. For that, we need the covariant and contravariant basis formulation. So that we get from this R hat and the capital R hat, small r hat and small capital R hat for the undeformed and deformed configuration. So, and the derivatives of R with respect to one and two directions are taken from the literature given by Simons. And these are they use a differential calculus Brenner-Serret formula to calculate the this relate these curvatures to the basis deformations. So where epsilon alpha beta is an inclined generalized stress, gamma alpha 3 is a transverse generalized strain, sorry, not stress. K alpha j is a deformed curvatures. So now these are all in plane. These strains are all in plane 2D strains. So we calculate the deformation gradient tensor using the covariant and contravariant basis formulations. From that we calculate the 2D strains. So the 2D strain is calculated from this formula. Gamma alpha is C into E alpha plus U comma alpha minus E alpha. So where gamma 1 is given by these strains, gamma 2 is given by these strains, E1 is a unit vector, U2 is also that. So a 2D curvature is calculated from this, where C is a the rotation matrix given by Rodriguez parameters. Rho. So rho is a Rodriguez parameter. They're given by 2 tan theta by 2 into the vector, where theta is the angle of rotation and the unit vector gives the rotation of an element with respect to that axis. So the rotation vector is a pseudo vector actually. Theta 1, theta 2, theta 3 means the unit vector of that gives the axis of rotation, and the magnitude of that vector gives the magnitude of rotation with respect to that axis. So this makes this pseudo vector very complicated actually. This we cannot just add two pseudo vectors just like two displacements. So there's a different geometry for that. We'll be seeing in the next coming slides. And I'm using Cauchy-Green strain to account for large deformations. These are 3D actually, 3D. So this is a 3D recovery strains because we were at 2D, and from 2D we have to come back to 3D actually. So, and this is a final Yo model that I'm where I'm applying one. Believe me, this is really complicated actually because we have 5 terms. I1 is trace of C, C is F transpose F, F is again the juxtaposition of contravariant to covariant vectors, and that is again the derivative of R hat and R. So before that, we need to select the small parameter. As I said, here 3D strains are selected as small parameter 0.1. So we order all the terms in the strain energy in terms of small parameters and neglect the higher order terms, apply the asymptotics. And unknown warpings are solved by minimizing the strain energy density function subject to constraints. So these are the constraints on warpings. That is the average of this angular bracket means the average of warpings through the thickness is 0. This is one constraint. And the moments of warpings through the thickness is also 0. These two constraints are applied, and we minimize the strain energy density function with respect to warping subject to these constraints. So finally, we will be able to solve warpings in terms of 2D strains. And this, if we substitute in the 3D strain energy, so and we integrate with respect to the thickness, so this will give the 2D strain energy, 3D strain energy in terms of 2D parameters. So this is the advantage of WAM actually. So these are the 0th order results of Capron. So W1, W2 was 0, and W2, W3 is given by this. So you can see it's a quadratic in X3 actually. So A, B are the parameters of the constants of this material. And first order results, these are going to be very huge actually. You get very huge expression. This is just first order warping. And if you see W3, then I don't know, you'll run out of this. W2 is this. And W3 is really, that is what, you know, no, that is what actually, contributing, because the gradients of these warpings do contribute actually, although they may be very small, but the gradient with respect to thickness will not be small. So it's very huge actually. So if you substitute this in the strain energy, then imagine the strain energies were very huge. And from this, we have to calculate the what you call the stiffness matrix and the internal force. Just in the symbolic form, it took 1 GB to just show this stiffness matrix. So one more, I think this will be a joke, actually. Joke and also reality also. What I showed here is just the 1/8 of what the warping I got in 3 days. Because if I show so big, then you see all molecules and atoms. Something more than that. So just to have the feel, I just gave that. Okay. Finally, I have to take forward that and do the 2D nonlinear surface analysis. For that, I need FEM elements. But the complexity is I have rotations also and the displacement. So 6 degree of freedom structure. Rotations are not so simple. These are the main culprits while updating the algorithm. So for that, we selected a special element called T63I element. What is that? Here, if you see at the left side, it's a triangular element with the 6 nodes, but only the corner nodes will have the displacements, and the interior nodes will have 6 degree of freedom, both displacements and the rotation. Why we are doing this? Because we want to reduce the complexity of handling the rotations and the compatibility with the other element. So if we can make it life simple, then can reduce this. We have to reduce this degrees of freedom of rotations. So these are the shape functions for quadratic uh, triangular element, shape function 1 to 6, and for displacements, I'm using only linear errors because that is only 3 elements. So this is how I'm formulating it. So this is a spatial discretization of displacements. This is for rotations. And we calculate the internal force vector from the derivative of strain energy with respect to u and theta. And the stiffness is the second derivative of strain energy with u's and thetas. With that, we linearize and try to form the Newton-Raphson form and calculate the delta u and delta theta. And we update it. Ui plus 1 is ui plus delta ui. But that the update of rotation is given by this Rodriguez formula. It's not so simple actually. So finally, I'm taking the plate and discretizing it. This is a sample thing, filled of elements, triangular elements, T63I. At the left, I am fixing it, and on the right, I am allowing only U1 degrees of freedom and stretching it. So let's see for a simple case. So then I calculate the mode shapes. How apply the force and get the stiffness matrix and do the eigenvalue analysis and see what are the mode shapes. So the lowest mode shape will be the first natural frequency of the system. So this is what I got. So I got two things very parallel to that. So one is a symmetric mode shape I got. So you can see this is a what you call this this is the length, and this is a cross section. So with respect to cross section, it is symmetric. This other thing is the asymmetric mode shape. So these are the interesting mode shapes that we got. But to get this, I have to run, so many days and all, because so long things are done. But believe me, this is actually asymptotically correct and without any assumptions. And this can be used in spacecraft applications where we have less prone to errors while in the numerical simulations. So I think this is my first part. I'm concluding it. So got the suitable materials, which are not limited to HEA. It can be used for any other application also. And mechanically characterize those and gave the constitutive modeling for that. And WAM was used for the wrinkle problem and gave the buckling mode shapes. So I acknowledge Professor Dinesh Haru Sampath sir, but sir, Professor Namrata Gudaya, Aritra Chatterjee, Nimesh Chahare, and Nilesh Lakshmikant Mane for helping me in the experiments, and Professor guiding me, and so many things. And I also thank Professor C.S. Jog and Professor Narasimhan Sinha for teaching me the mechanics of solids. And I thank all NMCADet, especially Rajesh, because he constantly motivates me. So a special thanks to Rajesh. And now I'll go for a part two. I don't know how much time I have taken. Oh, okay, right? I see people are sleeping actually because if you are boring, then I can stop. I don't know how to make it more interesting, but this is what I have done. So
Controversial aspects.
So part two is the delamination detection. This is also sleeping actually. So part two is the delamination detection in composite beams using modal analysis. This is done as a small uh, part of work in the department here. So here I'll be telling about motivation to do that introduction literature survey. What are the assumptions used? What is the theory behind this? What is the method, results, conclusion, and future work? Motivation is delamination. As we know, it's a very severe problem. Now we have to find out. It has to be monitored. So model analysis is really can be applied in a very simpler tool, like experimental tool, to apply and detect the damage in the structure. This is one of the structural, what you call this, non-destructive technique, model analysis. So now the objective is to identify the damage location in the beam, actually, because I'm uh, concentrating on beam using the simple non-destructive evaluation technique called model analysis. So damages are the discontinuities caused because of fatigue, impact, creep, and delamination is common. So structural health monitoring will keep the structure healthy and prevent the catastrophic failures. So we have to go for that. And what is SHM? It has four operations, four categories. One is the operational evaluation, data acquisition and cleansing, feature selection, and statistical model development. What is operational evaluation? Two questions have to be answered at this stage. One is, in what condition the system has to be monitored to get the best data. What is the condition of the system we have to take? Second thing is, what are the limitations on data acquisition? We cannot take the data every time. So we have to answer at this stage or the operational evaluation. Second thing is the data acquisition and cleansing. So here we have to answer uh, about the selection of sensors, what sensors have to be, what's the sensitivity, the quality, and where to put it. That's very important. The location of sensors and the number of sensors also. So, and the storage system hardware and cleansing. That is the data once we take from all these, answering all these, once we get the data. So how to select or reject the data, how good is the data. All this we have to answer here at this stage. Third stage is damage feature selection. We have to select a feature that gives uh, the damage indicator. Okay, that is called the damage indicator. So, and that we have to see if it is capable of distinguishing healthy and the damaged structure, whatever the indicator we have selected or the parameter. And is it unique to the structure and can we compute it experimentally, all these things. So finally, once we have got all these things, we should have a statistical model to represent the damage location. So you need to give that answer this. That model should give is the damage present in the structure and where is it present, how severity of damage. All this the model has to give that. So some model are there in the literature. Natural frequency-based methods, mode shape-based methods, FRF-based methods, wavelet transform-based methods, neural network-based methods. These are some literature methods. So I have used some assumptions here. System is homogeneous, elastic, and linear, and it is lightly damped. That is, damping ratio is very less. And Maxwell's reciprocal theorem is valid, and each mode of resonant frequency can be described by distinct poles. The poles are, distinct. They are not repeated. And the influence of one mode on the other is negligible. With these assumptions, we are going to, see just these three models are possible to represent: spatial model, modal model, and the response model. Spatial model is the mass. You give the specifications of the structure as a mass matrix, stiffness matrix, and the damping matrix. That is one. Second thing is as a frequencies, eigen frequencies, and the mode shapes. That is the second way of representing. Third one is as a frequency response function. So I'll be using frequency response approach here, frequency domain, and I used extended model parameters. What are they? They are derived from the models. Model, like just they derived quantities. So a residue, a feature called residue is used, and it is selected. It is seen that residue is unique to the structure. Okay, so if we are able to calculate the residue, then what I have found is the residue is very sensitive to the damage location. So what is residue? If you split the frequency response function into the partial fractions, the numerator is the residue. So these numerators are unique to the system. That is the observation, and we are making use of these residues to calculate the damage location. So residues can be related to mode shapes also using this. Finally, this is a FRF actually, frequency response function of one peak, let's say. The x-axis is frequency and the y-axis is the amplitude in dB. Let's say. So here I am showing the relation between the residue to the half bandwidth. So using this relation, I can calculate residues from the given FRF for a given mode shape. Okay, so this is 3 dB 3 dB bandwidth at this let's say a sigma and sigma are the bandwidths. So then the height of the peak is given by R by sigma, and R is what we are interested. Okay, and sigma is known to us. R, sigma, everything is known, but we are trying to calculate R and see that at various locations on the damage location, healthy location, and compare that R and give the damage location. That is the aim. So R is calculated using those relations. You can calculate the mode shapes from R also. That is what it is giving. So finally, the experiment, I'm using impulse hammer technique to do that. Hammering at 8 locations on the beam. 3 beams are taken. One is healthy. Other is delamination at 5 mm at fixed end, from the fixed end, and the delamination at 11.5 from the fixed end. It means one is at the middle, other is at the tip. Third one is a healthy structure. 3 beams I have. So how do I get that? Before that, the dimensions are 20.3 mm. Depth is 2.5 centimeter. Young's modulus is 120.3. And this is a GFRP composite, glass fiber reinforcement. And this is the configuration of plies. So this is how sample is prepared. We made a plate out out of GFRP and simulated the delamination using Teflon tape and cut into three beams. So this is a healthy beam, no delamination. This is a delamination at the middle, this at the tip. Now using these residues, whatever this I said, I have to hammer it at different locations. Just by hammering, I have to give the damage location. That is it. And this is an experimental setup, data acquisition system. This is a beam and it is clamped here. Impulse hammer, you can see the miniature impulse hammer, and the accelerometer is kept at the tip. So this is how the impulse signal looks without windowing signal processing. Or you have to do signal processing, then you get this just filtering the data. And the acceleration time response signal is this from the accelerometer. So you take the FRF and get the the peaks. So these peaks will speak about the frequencies, first frequency, second, third, fourth. Now you are interested at the first peak, okay? And from there you calculate the residue of the first peak. So these are the frequencies where I got the peaks for different things. Because of the defection, that is a delamination, the frequencies are reduced, that you can see. That is a natural thing. But now this is interesting actually. If I plot I used a statistical model, that is a difference of residues. I just plotted the residues difference at different locations, at the same locations of all three beams for healthy and mid defective beam. So this is a mid defective beam. So I have to have a peak at the middle. Then it will say that this is a the location of damage. But this is just first mode. So similarly, for the comparing the healthy and the tip defective, I have to get the peak at the end, but I am not getting. Let's see for the second mode. So for second mode, I almost got it. So at the middle, I got the peak and the at the tip also. So for third mode, almost it's giving almost the correct location, the peak. So this is a very good experiment of just tapping and giving the damage location. Where is it damage? But for that, we need to have a healthy structure. That is over the time before structure is put to the function. We need to have the impulses, signatures that we compare over the time. Then this technique will give the damage location. So finally, I have done the damage location, and higher order modes are highly sensitive to damage. That's what I consider. So we can extend this to plates and shells. So thank you. So questions and answers also, you can give answer.
So the other 7 of the equation B3.
Yeah. I can show you on my desktop. That's more interesting.
Why assumption that is linear denomination?
Because here those the relations that are related to the residue and those 3 dB bandwidth, they are okay with in linear only. If it is non-linear, then they are non-linear. Yeah, time is fine.
I have a question. On this last part, with for the second part, with the lamination, that you almost got the location of the damage.
Yeah.
Do you think that was because of the, experimental testings?
Yeah.
Because of that, or maybe that you had to go to an even higher order mode because you checked 1, 2, 3. Right?
Yeah. I could have checked fourth and fifth mode.
Yeah.
But because second was almost giving the shape, and third almost gave it.
Yeah.
So the sequence was like low to high. So I stopped at 3, and this was done quite long back. This work. So 3 was almost promising. We can do it for higher because you can see, I think 6 peaks are there in the FRF. You can go till 6 and more also. It is possible. Okay.
Thank you, Khaja.